Ok, bom dia para todo mundo. Good morning, everybody. Então, hoje a gente tem o prazer de poder falar com o professor Giovanni Chirilli, da Universidade de Regensburg. Ele fez o doutorado dele com Ian Balitsky e ele está interessado no limite de altas energias dos espalhamentos que são dominados pela cromodinâmica quântica. A gente já tem uma teoria estabelecida da cromodinâmica quântica, só que agora a gente tem que estudar as aplicações, os fenômenos coletivos e a emergência de novos fenômenos e novos modelos efetivos. E um dos casos muito interessantes é o formalismo de polos de cor, e tem várias aplicações, como a gente vai ver hoje, e esse formalismo tem recebido grandes contribuições, em ordem seguinte a dominante, do professor Giovanni Chirilli. Então, hoje, ele vai falar um pouquinho para a gente sobre isso. So, Giovanni, it's a pleasure to have you here, albeit online, and we are all eager to learn a little bit more about your work on this high-energy frontier of QCD. Okay? So, please, can you start your talk?
Thank you. Thanks a lot for the invitation. I'm very happy to be here giving a talk for this seminar session. So I would like to talk about high energy dynamics with sub-eikonal corrections. And first, let me start with the outline. I will start with some introduction on high energy high density QCD scattering processes. And then introduce a little bit the notion of BFKL equation and its evaluation of unitarity. Then I will move on to explain the formalism of high energy operator product expansion and the associated factorization in a rapidity space. And then I will talk about the leading and next leading order evolution equation, which describe the dynamics for unpolarized scattering at these high energy, high density processes. And the last topic is the subject I'm working on currently, and it's about high energy spin dynamics, which is an extension of the high energy operator product expansion, including sub-eikonal correction. So, what would like to understand on the broad sense is the structure of hadron, and in particular the structure of hadrons at high energy in the center of mass. And we know that from general ground, the scattering processes, for example, for proton-proton, have a cross-section which behaves at high energy as a log of a square of energy. And we will see that this log square of energy in perturbation theory is violated. We would like to understand also if the coefficient in front of this universal behavior is indeed independent on the type of hadrons that we scatter. And if we consider, for example, the specific case of deep enlace scattering, we would like to know how the cross-section behaves when we increase the center of mass and we fix the resolution of the virtual photon exchanged in these processes. In this type of collision of deep enlace scattering, we know that the parton density can rise, but we also know that it cannot rise forever because it has to respect to unitarity, and we would like to know what is this limit. And indeed, we know that the cross-section is limited by 2 times the area of the scattering area of the nucleus. And to describe these processes, we would like to understand what are the proper degree of freedoms. Moreover, there is a long-standing problem, which is the one of calculating the gluon produced in nucleus-nucleus collisions. So this type of result would be important because when we scatter 2 large nuclei, for a very short amount of time, there is a quark-gluon plasma which is created, and then the evolution of this quark-gluon plasma to hadronization is usually described with hydrodynamics, successfully described with hydrodynamics model. But the hydrodynamics model needs an initial condition, and the hope is that one day this initial condition is calculated analytically from first principle in QCD. This type of physics is studied in accelerator facilities like at RHIC, where they scatter gold-gold or proton-gold collisions, or at LHC, where the scattering is of heavy ion lead-lead or proton-lead collisions. There are also futures experiments like the Electron Ion Collider at Brookhaven, and also the Large Hadron Electron Collider at CERN. Okay, so if we consider the differential cross-section and we consider it in the laboratory frame, the differential cross-section to detect a final lepton, so we are considering a lepton scattering on a proton very deeply, and the differential cross-section can be written in terms of the differential angle and the infinitesimal final energy of the scattered lepton, and is given as a convolution of the leptonic tensor with the hadronic tensor. Here, M represents the mass of the target, usually proton, but it could be also a large nuclei. And we indicate with the P mu, capital P mu, the momentum of the proton, and with the Q, the momentum of the virtual photon exchanged in these processes. X Bjorken is the parameter which is in the first approximation the amount of momentum carried by the partons during this scattering. And the P1 and P2 are light cone vectors. We are interested in the situation in which this parameter X Bjorken is very small. And that's why we called small x physics. But let's see a little bit more in detail. The hadronic tensor is usually parameterized through the structure function. In the unpolarized case, the structure functions are F1 and F2. And if we consider polarized scattering processes, then one has to consider structure function G1 and G2. In this case, the hadronic tensor would be antisymmetric. And in order to study this structure function, this unpolarized structure function, then the leptonic tensor itself has to be antisymmetric. And this means that also the incoming beam has to be polarized. We will see in the first part of the talk how to study the behavior of this structure function in the unpolarized case. And in the second part, I will present the formalism which I plan to use to study the behavior of G1 structure function for polarized case indeed. So usually what is actually considered is the imaginary part of the T product of the two electromagnetic current with the help of the optical theorem. And and this is the object which is usually considered. It is always, this kind of approach is always considered usually in two different limits. And these two different limits highlight two different behavior of the target. If we consider the Bjorken limit, in the Bjorken limit, the virtual photon in this deep energy scattering process interact incoherently with one of the constituent of the target, while the constituent of the target themselves interact very weakly. In this case, the X Bjorken is a fixed parameter, and the in perturbation theory, one has to resume large logarithm of the type of Q square, which is the virtuality of the photon, which establishes the resolution of the entities inside the target, divided by the non-perturbative scale. On the other hand, if we consider a high energy range limit, then the scattering is coherent because the density of constituent inside the target is very high. Because of this, it is more suitable to consider a different frame, the so-called dipole frame, in which the virtual photon split in a quark-antiquark pair long before scattering off the target. And in this way, the interaction with the coherent interaction with the target can be better studied. In this case, the virtuality of the photon, so the resolution of the photon is fixed, and the center of mass energy, by center of mass we mean the center of mass of the system between the virtual photon and proton, here is S, this understand variable. Then this S becomes very large, and therefore X Bjorken is going to 0, and therefore the important logarithm that one has to resolve are of the type alpha S log of X Bjorken. So what we are mainly considering in this talk is this right side of coherent interactions. So let's see in a bit more detail. If we consider a braid frame, then the resolution of the virtual photon can be associated with the inverse of its momentum, and it resolves inside the target parton which are of the size of the wavelength of the virtual photon in the transverse space. So if we keep this in mind, we can consider these two regimes, the Bjorken limit and the Regge limit. Let's start with the first. If we consider the Bjorken limit, then the resolution of the virtual photon, because both Q and S are going to be considered very large, so that X Bjorken is fixed. Then while the resolution increases, we resolve in the target a smaller and smaller quantity, although the number of constituents increase. But the density does not increase because the size in the transfer space decreases. This evolution is the evolution from left to right of the target, is described by Diglap evolution equation. On the other hand, if we fix the momentum transfer, therefore we fix the resolution, and we keep increasing the energy, therefore we resolve, increasing the energy, we resolve more and more partons inside the target. Then we resolve more and more partons of the same size until some point to which the target appears to be saturated, and we enter in the saturation region. The evolution of the target towards a higher energy with fixed resolution is described by the BFKL equation. When the density becomes very high, then we need the new evolution equation, which has nonlinear terms which describe the recombination processes needed to tame the growth of the cross-section above the unitarity limit. This behavior is also been observed in experiment, where it is observed that the main degree of freedom at this small x, so high energies, is the gluons, are the gluons. In this plot, you can observe that the gluons are scaled by factor of 20 respect to the valence quark. So the smaller is the X Bjorken, so we are going in this direction. The more the gluon dominate the dynamics at this regime. So if we consider then this high energy mass limit, high center mass limit, then as usual, let's indicate with S the Mandelstam variable. Lambda QCD is the non-perturbative parameter, and T the Mandelstam variable. Then the Regge limit is achieved when this S, the Mandelstam variable, is much greater than lambda QCD and the T transverse. In this case, as we have mentioned earlier, alpha S log of this large parameter is order 1, therefore it needs to be resummed. And the typical diagram for this leading log resummation are this ladder diagram. The more ladder horizontal gluon you add, the more this n parameter increase, but they are always order 1, therefore they need to be resummed. And this resummation is done through the BFKL evolution equation. So BFKL evolution equation, when it is applied, for example, to onion scattering, predicts that, so suppose you have a quark, anti-quark, scattering quark, anti-quark, then just by power counting, we see that the full cross-section has to have the dimension of a distance square, so it's proportional to the only available distance here is the size, transverse size of the first onia times the transverse size of the second onia. Then we have alpha squared due to this 4 coupling with the onia, the gluon with the onia. And then all this resummation, this ladder diagram, is encoded in this exponentiation, which is given by the solution of the BFKL equation. It turns out that this parameter is greater than 0. This means that the higher is the energy, the more this cross-section increases with the energy exponentially. Now, let's consider this case in deep lattice scattering. So imagine that the first transverse distance is given by the inverse of the virtuality of the photon. And that the size of the second onia is the radius of the hadron, the target. Then the cross-section is rewritten in terms of this new parameter, R and Q. And if we impose that the cross-section does not violate this black disk limit, then we solve for Q, and we automatically get an intrinsic scale, which is the saturation scale, which grows with increasing energy. So we see that when we increase energy, X Bjork can decrease, this quantity becomes very large, and this saturation scale increase. And that's why in this diagram, we see that this is a saturation line which increase with energy. So if we consider the virtuality of the photon less than the saturation scale, we have violation of unitarity. So in all we are considering, the virtuality of the photon is going to be bigger than this saturation scale. If we plot the DIS cross-section, for example, in terms as a function of the center of mass energy, we see that BFKL, as we have seen in the previous slides, predicts that the cross-section grows exponentially, and indeed this BFKL predicts nicely the pre-asymptotic behavior of this cross-section. But we know that, as we mentioned in the introduction, Froissart bound tell us that the cross-section should not grow higher, faster than log square of energy. Moreover, we know that this cross-section cannot grow forever, because unitarity means conservation of probability. So we don't want that the probability to have a scattering is greater than 1. And to restore this unitarity, we see that there is a new mechanism, that there is a nonlinear dynamics, which is important when we go to this regime, and that this is encoded in the evolution equation. So the BFKL equation tells us how the hadronic target evolve in this pre-asymptotic behavior. And as we will see, this unitarity is preserved by including nonlinear terms in this evolution equation. How to include this nonlinear term is the subject of the next few slides. So if we consider leading log approximation in a deep lattice scattering, Then we have the virtual photon, which split in a quark-antiquark pair and interact with the target. And we have the usual BFKL ladder, which needs to be resummed as we mentioned before. If we consider the diagram where the virtual photon interacts directly with one of the quark, this type of diagram is energy suppressed, and it is important in the Bjorken limit, but also important when we are going to consider the spin dynamics at high energies. Okay, so the next step, before I introduce the energy operator plot expansion, is to consider to remind the light cone expansion in light rate operator, and then we're going to answer what are the relevant operators at high energies, and then we consider the energy operator plot expansion. So if we consider the Bjorken limit, then the T product of two electromagnetic current is usually factorized in terms of a coefficient function by introducing a factorization scale in transverse momentum and matrix element of this light rate operator, non-local operator. So in this way, the perturbative calculable object are this coefficient function, which can be calculated order by order. And then the matrix element can be calculated in a background field method and give us the evolution with respect to this parameter. And this evolution with respect to this parameter is nothing but Diglap evolution equation. This is a well-known procedure. Now, let's consider high energy. And let's consider the propagation of a particle inside from a quantum mechanical point of view. This particle is propagating at very high energy. Then the wave function in the vacuum can be approximated by the wave function in the vacuum multiplied by this exponential of the external potential. This is the WKB approximation. Now imagine that instead of an external potential and instead of being quantum mechanics, we are in electrodynamics. If we are in electrodynamics, then this free wave function is corrected by a phase factor by exponentiating the gauge field. On the other hand, if we are in QCD, this exponentiation is not a trivial exponentiation, rather is a path-ordered exponential, because now the gauge field, as we know, is a matrix in the color space. Therefore, the gauge field does not commute a different point, and therefore it's a path-ordered exponential. And that are the main degree of freedom or the main operator that we need to use to describe high energy scattering in QCD. So let's consider then the scattering or the propagation of a particle in an external field. And we consider a specific frame, the frame in which the particle is still very energetic, but we boost the field such that it is reduced to a shock wave shape. So therefore, the particle is propagating in this thin shock wave. Then, because we can we have that the field strength tensor outside the shock wave is 0, then the gauge field outside the shock wave is a pure gauge, and it can be gauged away. And the propagation of, say, for example, a quark in this external field reduce in a free propagation from point X until the interaction with the shock wave. Then we have the interaction with the shock wave, which is given by this exponential factor. Now, this exponential factor actually lives in this tiny longitudinal distance. However, because outside the gauge field that's being gauged away is 0, then we can extend the limit of integration from minus infinity to plus infinity. And that's why at a high energy, the path order exponential becomes an infinite Wilson line, an infinite gauge link, and it is at fixed transverse position. And then we have, after the interaction with the target, we have again propagation, free propagation from the point of interaction of the shock wave until the end point. So if we consider this approach, this semi-classical approach to study the T product of two electromagnetic currents, then we see that introducing a factorization parameter. Now, the factorization parameter here in this high energy processes is the rapidity, is the energy. So all the fields are ordered in this process in a rapidity space. And if we introduce a rapidity factorization in rapidity, then we separate the fields which are quantum when the rapidity is greater than this factorization point. And the rapidity below this factorization point is the background field. So all the fields below this dashed line is this red band, which shrink into a shock wave. Therefore, we have to study the propagation, for example, a virtual photon which is split in a quark-antiquark pair in the background of this external field. Here, all these gluons and quarks are quantum, and therefore, since we are using perturbation theory, we consider these partons one by one. So in first approximation, we have only quark-antiquark pair. In the second approximation, we have a quark and a gluon, and so on. Now, if we consider the T product of two electromagnetic current in this target in this target state, which is a proton or a large nuclei, then we see that the full hadronic tensor can be expanded in terms of coefficient function and convoluted with the matrix element of the relevant operator, which are these infinite Wilson line. So if we have only quark-antiquark, then we have only two Wilson line and a Wilson line that adjoint conjugated for the antiquark. Then if we have quark-antiquark gluon, then we have more Wilson line in the matrix element and a new impact factor. Therefore, the full hadronic tensor is expanded in terms of coefficient function, like we did in the Bjork limit, and the matrix element of this operator, which are infinite Wilson line. So the full high energy dynamics is encoded in this Wilson line. So let us consider, for example, the leading order in the leading log approximation. Then the DIS amplitude is given by this leading order impact factor and convoluted by the matrix element of this Wilson line. This impact factor in a coordinate space is very well known for a long time, and it can be written in terms of conformal vectors operators, and it satisfies the nice property of gauge invariance and conformal invariance. One can check, for example, that if you take the expression in coordinate space and make this inversion, which is one of the transformation of the SL2C conformal group, Mobius group, then this object is invariant. Now let's consider the matrix element. We would like to understand how this matrix element evolve with energy, because we would like to know how to resum this log of energy from a semi-classical point of view. So we consider this operator, which are these two Wilson lines, and these two Wilson lines are renormalized at a starting rapidity point at 1. Now, this rapidity at 1 enters inside the Wilson line in two different ways. One is regularization by slope, meaning that the particle which is propagating inside this external field is not infinitely energetic, but is as a finite energy. Indeed, as we can see here, if the energy of the particle is infinite, then the full Wilson line lies on one of the light cone. But because the particle has no infinite energy, then there is a dependence on the rapidity and on the second light cone. An alternative approach is to consider a rigid cutoff for the momentum space for the gluon longitudinal momentum. Okay, so the question is how this operator evolve with rapidity. This to understand this, one has to apply the background field method. So we ask ourselves how this operator evolve when we go from a starting rapidity point eta 1 to a second rapidity point eta 2. So the idea is to divide the fields in quantum and classical. The field with classical are all the fields which are below this rapidity point eta 2. And the quantum field are the fields with rapidity between eta 1 and eta 2. And since these are quantum fields, we functionally integrate over these fields. And after this functional integration, we get a coefficient. And this coefficient is convoluted with all the fields which have been left classically. And these are Wilson line again at the new rapidity parameter eta 2. So we see that this relation between the starting rapidity eta 1 and the end rapidity eta 2 is a relation that can be either linear or non-linear. So we get either linear evolution of this operator or non-linear evolution in case these operators are multiplying and they are the same. So let's suppose, for example, we take one Wilson line. We take one Wilson line, which is normalized at eta 1. We split in quantum and classical. We integrate over the quantum field, which is now represented here by this blue gluon. We have three diagrams to resum. And after we resum these three diagrams, we end up with this evolution equation where the coefficient here is the kernel of the evolution. And it is proportional to this infinitesimal step in rapidity. And it is multiplied by the new matrix element of a new Wilson line. As we can see, we have product of Wilson line. So therefore, this relation is nonlinear. So if we consider the trace, so color singlet object like a virtual photon for DIS, and we consider the evolution with respect to rapidity of this object, we have to resum this diagram, at least for the real case. Then we have also the case where the gluon does not cut the shock wave. But anyway, resuming all this diagram, then we get a nonlinear evolution equation, which is given here in terms of this operator U calligraphic, which is nothing but rewriting the evolution equation in terms of the T matrix rather than the S matrix. Here, the linear terms reproduce the leading log resummation given by the FKL. On the other hand, this nonlinear term is the nonlinear term which takes into account the resummation, the nonlinear term which takes into account the recombination process, which is important to restore unitarity. Okay, so there is a nice property of this conformal BK equation, which is as for the impact factor is SL2C Morbius invariance. Indeed, if we consider the infinite gauge link, this Wilson line, and we perform an inversion, then the Wilson line remains invariant. If we apply this transformation to the full equation, we see that the equation itself is a conformal invariant. So this is a nice property which is helpful when one calculates next reading order. So indeed, why we are interested in calculating the next leading order? The reason is that once you have an evolution equation, leading orders, you want to know what are the region of applicability of this evolution equation. Therefore, you want to size the high order correction, whether they are important or how much they are important. And moreover, the evolution equation that we have seen has a fixed argument of the coupling constant. Only going to higher order, we can determine this argument. From a formal point of view, one can also check going in next leading order the conformal invariance by considering a supersymmetric Young means in n equal to 4. Okay, so when we go to next leading order for the full DIS amplitude, one has to consider next leading order for the evolution equation and next leading order for the impact factor. So the NLO BFKL type of contribution are given by this leading log summation multiplied by the next alpha. However, when we calculate NLO impact factor, there is a little caveat because they contain a leading order resummation which have been already resummed by the leading order BFKL equation. So there is a nice way to separate these contributions which are already resummed in the leading order BFKL equation, which contaminate the pure next leading order impact factor. And this is done through the operator plot expansion formalism, satisfying or requiring order by order that conformal invariance is preserved. Indeed, this extra term with this energy dependence in the NLO impact factor would violate the conformal invariance of the impact factor. So restoring this conformal invariance is a procedure which tells us how to shift all the energy dependence of the impact factor inside the evolution equation, and therefore you have a bookkeeping in order to calculate systematically the amplitude order by order. Okay, so if the first line, as we saw, is the leading order, the leading order contribution, then at next leading order we have this impact factor, which is convoluted with this matrix element, which is not anymore a dipole. This is the diagram which I've considered for the leading order, and this is the diagram for the next leading order impact factors. I will show the result only for the linear case, in the sense that this result is a Fourier transform of the case where this evolution here is in the BFKL limit. And it is fully in a momentum space. This was a long-standing problem, and in the usual or conventional perturbative QCD, after a long calculation by several groups, this result unfortunately was not provided in a form that is implementable in phenomenological studies. And instead, this is a nice compact form of this Fourier transform of the impact factors. An application of this was the calculation of the next leading order gamma star scattering, fully analytic. So now let's consider the evolution equation. The leading order evolution equation has this dipole type of kernel, and then we have to add this extra coefficient, which are one is proportional to the usual to the leading order matrix element because it's just a running coupling correction, and then there are other contributions which are not in the running coupling, but these are still NLO correction to the evolution equation. So there are some diagrams to be calculated. Here, these are for the running coupling type of diagram. And okay, one has to resum this type of diagram. If we consider Young-Mills theory, then we have also diagram with the Bluino and a scalar. And if we consider this diagram then in n equal to 4, for example, and considering this composite conformal operator, it's a kind of a counter term which restores the conformal invariance of the evolution equation. Then the evolution equation n equal to 4 is this nice form, conformally invariant. And in QCD, the result is the following. We have this blue term, which are the running coupling contribution. And then we have the next terms, which are conformal, divided in two types, non-analytic in the J space and the conformal analytic, meaning that this red contribution completely agree with the n equal to 4 calculation. So this equation fully agrees with the Fadin-Lipatov in the point of linearization. So if you take this evolution equation, which is clearly nonlinear, and you linearized to match with the NLO of the FKL, then we have fully agreement. Now, if you scatter, for example, proton-nucleus or nucleus-nucleus collision, besides of the dipole, which is relevant for GIS, then you have also quadrupole. And if you want to study this cross-section at next leading order, then you have to consider the evolution equation not only of a dipole, but also of quadrupole or sextupole. And in this case, at next leading order, there are new diagrams to be considered. And this is also being considered, and they go by the name JIMWLK evolution equation. Okay, so far I have talked about my past research activity, and now I don't know how much time I'm left.
Oh, we started a little bit late, so I guess we still have like 20 minutes to end, something like that.
Okay, I think I'm going to need even less than that. So very good. Okay, so the next part of the talk is based on my two recent papers, and it is about considering sub-eikonal corrections. So all the studies in high energy QCD at small x at least done so far, they are based on this eikonal approximation, which we discussed before. You get an infinite Wilson line. So if you consider the quark propagator in this shock wave external field, then the first contribution is this operator, which is the infinite Wilson line we considered before. But as we mentioned at the beginning, when I showed the Adronic Tensor, and we said that we would like to study the polarized structure function, we said that we have to consider the antisymmetric term of the Adronic Tensor, so that it will be convoluted with the antisymmetric term of the leptonic tensor. So if we would like to get a non-symmetric term in the Adronic tensor, then this eikonal contribution, infinite Wilson line, in the quark propagator is not enough. What is necessary is to consider deviation from this straight line, infinite Wilson line, and consider also sub-eikonal correction. And this sub-eikonal correction comes in with the new operator of the quark type and of gluon type. Here we have this calligraphic F and calligraphic Q, which are defined here. We have this semi-infinite Wilson line until the point where we have this new operator, psi. And then we have a gauge link in the adjoint representation. And then we have psi bar. And then again, infinite Wilson line in the fundamental representation. On the other hand, this F calligraphic is an operator which starts as an semi-infinite Wilson line. Then we have this insertion of Fij operator, field strength tensor. And then we have again a semi-infinite Wilson line to minus infinity. So all the work that we have done until the previous slide with this term only has to be repeated, hopefully one day also to next in order, including this new operator. So this is diagrammatic representation of this operator. And this is the impact factor with this new operator. So this impact factor is just a virtual photon split in a quark-antiquark pair, and it propagates into the external target highly boosted. So until now, this operator was absent, and you would get simply two Wilson lines. One Wilson line for the quark and a joint conjugated Wilson line for the antiquark. Now we have the insertion of this sub-eikonal correction, and therefore we need new impact factors, which is given here, and it is actually a sum of two contributions. One sub-eikonal contribution is related to energy suppressed for unpolarized case, but then we have energy suppressed contribution which are relevant for polarized case. Indeed, the polarized contribution are energy suppressed with respect to the unpolarized one. This impact factor has been calculated. Is here I1 is for the unpolarized case. This I5 is for the polarized case. Of course, we have considered only the quark, but then we have also Fij impact factor. But it turns out that this Fij give exactly the same impact factor as with the quark, but this is indeed not surprising because they have the same parity property. And if we put things together up to sub-eikonal correction, we have the T matrix of two electromagnetic current expanded in terms of coefficient function, convoluted with the unpolarized case, and the energy suppressed contribution for the unpolarized case. And then we have this new impact factor, which convolute with the new operator, of which one has to consider evolution equation. So if we want to know the dynamics of the hadronic target for polarized case, so spin dynamics, then one has to consider the evolution of this new operator and convolute with this new impact factor in order to study polarized structure function like G1. So here is the expression of this coefficient, which I showed you here in this expansion. The nice property, as I mentioned before, of this is again gauge invariants. They are electromagnetic gauge invariant, and they are also Mobius invariant. In this process, one introduced a new quark and gluon distribution. Indeed, if we parameterize this matrix element with this the insertion of this new operator, we get a new quark distribution, and this Q1 is for the unpolarized case, and this Q5 is for the polarized case. And we have also gluon distribution, the longitudinal and transverse case. Then, if we consider, for example, one of these operators, we have to consider the evolution of this operator, and the evolution of this operator is given diagrammatically by these two diagrams. The sum of these two diagrams is again done in the background field method. I will not go in the detail of the process of obtaining this, but as you can see, always blue line are the quantum field and the red line are the classical field. So after one loop, so you start with this operator, so you have these two are the starting operator, then you functionally integrate, meaning that you take contraction of this quark antiquark, but you do this contraction in the external field, And when you do this contraction in the external field, you are going to pick up the sub-eikonal contribution in order to get evolution of the starting operator. So after one loop, you get back the same operator, but also new operators. So the evolution equation is more complicated. So this is for the unpolarized case, and this is for the polarized case. So the idea is that the energy dependence of polarized structure function is encoded by the evolution equation of these operators. So if we consider, for example, the evolution equation of this type of object, then we have another evolution equations. I'm just going to flash the results here, but if we consider the insertion of Fij in the dipole, then these are BK type of diagram, but with the insertion of this new operator Fij in the background field or the quark, anti-quark field operator. And when you resum this diagram, then you get this type of evolution equation. And these are just a sample of evolution equation that one obtains. Okay, so I think I reached the conclusion. I have shown you that linear evolution equation not able to describe dynamics of high energy. We need nonlinear terms to restore unitarity. And these nonlinear terms are obtained in the semi-classical point of view with the background field method and the operator product expansion. And we got nonlinear evolution equation, which are the BK-JIMWLK evolution equation. So this evolution equation encodes the dynamics of the scattering processes at high energies. Then, with the help of this OP, we have calculated the NLO photon impact factor and the NLO BK evolution equation. Now, in the second part of the talk, I have shown you the extension of this operator product expansion, including sub-eikonal contribution, which are important for polarized structure function. So we have obtained a new impact factor, new evolution equation, new quark and gluon distribution. The meaning of them is still not clear, and is the subject of further studies. As a short outlook in this direction, one has to extract double log of energy contribution. Indeed, in the evolution of polarized structure function, the main contribution is not a single log of energy, rather is a double log of energy contribution. So you have alpha S times log square of energy, which is kind of different than the unpolarized case where you have a single log. So this double log of energy for polarized structure function has been originally considered by Bartels and RHIC. And one hope to reconcile this result with the Wilson line approach. Of course, the goal is not to reproduce known result, rather is to extend this result to nonlinear physics, like BK has extended the BFK equation. Then one would like, obviously, to compare with the result which have been obtained by other groups, like Kovchekov's group. They have done similar studies, but their study, they have found discrepancy with the known result by Bartels and RHIC. There is also a result by Bussari, Hatta, and Yuan, and they have considered orbital angular momentum at small x. And moreover, one would like to, in the polarized case at least, would like to consider the matching with the next-to-next leading order calculation by Mockver, Masseran, and Vogt, and perhaps extend this formalism also to other observables. And I think I conclude here. Thank you.
Okay, thank you very much for this nice talk. Let's see if the students and the other members have questions. Okay, Rafael, please go ahead.
Hi, Professor. Thank you for your talk. I'm wondering, what's the main idea of the background field method? I don't know that.
So the idea, the main idea is to consider evolution of an operator. So if I go to the page, maybe I was too quick here, I think. So the idea is the following. You would like to know that, okay, suppose you are here and we have done our study of this object. We know this object is related to the DIS cross-section. And we consider the propagation of this quark-antiquark in this target state. And the idea of the background field method is to consider the process from a semi-classical point of view by separating the quantum fluctuation from the classical fluctuation, which is a kind of application of the Wilsonian renormalization group. So if you consider the if you know that there is a parameter that split your fields in a quantum and classical, you can certainly, function integrate over the quantum field, meaning that you create Feynman diagrams. If you are in the vacuum, you just create a quark-antiquark scattering, gluon-gluon scattering, and so on, right? But if there is a parameter which tells you that part of the fields are quantum and other are classical, then you have to consider this quantum fluctuation, this quantum, this functional integration in the background of the classical fields. So the quark and gluon propagator are not the usual quark gluon propagator, but they are in this background, the background field. And if we consider this quark-antiquark, for example, in the background of the target, so imagine that you have a target which is a proton. We know that the main degree of freedom of proton are gluons, so you have to start with considering the quark-antiquark propagating in the gluon. You neglect as a first approximation the detail of the target. You say my target is made only by gluon in first approximation. Then you consider the propagation of these particles in this external field. But then you remember that this is an approximation. You get your operator, which are Wilson line, and you re-evaluate your operator in the target state. And this was your approximation. You first highlight your main operator, and then you remember that this was just an approximation, so you evaluate this operator in the target state. So if you now have a model, for example, the GBW model is a famous model, you convolute with the impact factor, you get your cross-section. You can fit with data. But this is not enough, because if you want to know the energy dependence, then you first find the energy dependence of this matrix element, resum, or if you wish, calculate the evolution of this operator from one rapidity point to the other rapidity point, meaning that you know how this operator depends on energy. And so you encode in your cross-section the energy dependence. And then after you do this, you can convolute again with the model.
Thanks, Professor. It's very enlightening.
Okay.
Okay. Raimon, do you want to ask your question?
Okay. Thank you, Giovanni, for the seminar. For my question will be like, you mentioned that you probably want to study other observable. What will be then? And are they related to the Electron Ion Collider or something like that?
Yes, they are related like other observable. I meant other processes. For example, this sub-eikonal contribution are important also in a proton-nucleus collision. For example, you can encode a sub-eikonal correction also there. By other observable, I also meant that there is this orbital angular momentum studied by other groups, and perhaps this approach can be considered to extend to nonlinear contribution, but mainly proton nucleus collision is certainly one that has to be considered.
I see. Thank you very much.
Okay, I have one question. Can you go back, please, to page 51? Oh, sorry. So it's not 51, maybe 52. Is the one with the new result with the... Yes. So this is the main new result, right?
Well, all these evolution equations, I didn't put them all, but also these.
Yes.
These are all the new evolution equations. Yes.
Okay, but then I look at that one. It's very similar to the leading order, right? Evolution, right?
This space.
Yes.
So you see here, I didn't mention something. So here we start with this object, which is parity odd, and we end up with this operator here, which is parity odd. But there is also this operator, which is defined here, which is parity even. But this valuation of parity is only, it's not a real valuation, because this object is convoluted with, is multiplied by this tensor-like object, which restore parity and to be, again, parity odd. And there are some contributions which resemble the leading order BK equation, you mean, right? I didn't include it here, but definitely there are contributions where, for example, if this object is considered completely classical, then this object, this operator, is not here. And then you get a completely BK equation with the addition of this operator due to sub-eikonal contribution. But here is not quite. Sorry, I'm going back. This is not quite the BK, right? And then here you have F, and here you have calligraphical Q.
Yeah, so just to summarize, in DGLAP you usually have the singlet, and then you have the gluon evolution, and then maybe you can add at the next leading order or next to next leading order, you have to put some other distributions. At this point, how many distributions do we need in this approach? Of course, we are going to need the dipole distribution, but also do we need a quadrupole distribution if we're going to do a fit, or do we need a different distribution for the quarks? And depending on the spin, we need spin up and spin down distributions.
Well, in principle, these are the distributions that I find. You see,
okay, how many of them are there?
So, for example, these are the distributions that I find in the IS case. And for G1, yes. And you see here you have a dipole, but it's multiplied by this Q1, which is nothing but Q1 is yes, Q1 is just this object with the insertion of gamma minus, if you wish. Okay. So how many are there? Well, let's count. 2. Okay, so these Q1 are for this quark distribution are for the unpolarized case, and this is not only unpolarized case, but these are energy suppressed. So you know that in QCD at high energy, the gluon distribution are the one that dominates, right?
Yes, yes, yes.
And we also know that the quark distribution are suppressed.
Yes, yes.
As energy suppressed. So this would be the energy suppressed quark distribution in the unpolarized case. Then in the polarized case, there are this quark distribution where 5 means that there is insertion of gamma 5. 1 here means that there is insertion of gamma minus, also called P1/ in my language, but it's gamma minus. And then you see that you have 4, and then you have these 2 gluon distributions.
Right.
Because you see the operator is not anymore a simple dipole, but it's a dipole with the insertion of an operator.
Yes. So you would need 2 distributions in the if you neglect quarks, you would need 2 gluon distributions.
Well, here you have longitudinal distribution and transverse distribution.
Yeah. And okay, let's see. Does anybody else have another question?
No questions.
Okay, so let me ask another question. So you say, of course, you can do a fit like a GBW did to leading order, okay? But are most people using these next leading order impact factors? And if they are not, why they are not using it?
Okay, so the impact factor that they are using actually is here. I just showed you. So the impact factor that I showed you here is the impact factor for BFKL, right? You have NLO impact factor here, and then you attach leading order BFKL. Then you need NLO impact factor. Sorry, you need NLO impact factor with the leading order BFKL, and the NLO evolution equation with the leading order impact factor. You don't want to exceed the precision, right? So in the case of nonlinear physics, I didn't show you the result. This is only because it's in the momentum space. It was quite long calculation, but in the nonlinear case, we also have a result. But actually, there is also a result by Guillaume Buff. And they have calculated this within this hybrid model where they don't use the language of operator product expansion. Rather, they have this virtual photon split in a quark anti-quark, interact with the shock wave, but they leave open, then they convolute, square it, and so on. And they have implemented this. They have used this recently. They have considered the full NLO impact factor, NLO BK equation. And okay, there was a long-standing issue about how to modify the NLO BK equation with a different rapidity parameter. But then it turns out that the rapidity parameter that we chose with Jan is the one that gives the same result. So there was an issue there, but then I don't think there was further development, because all these different evolution equations with different parameters gave the same result. But yes, it was implemented. It was implemented. Yeah.
Okay. And well, perhaps one last question then. If you take the collinear factorization, when you go to next leading order, you have factorization scale uncertainty, and usually you multiply by the scale by 2 and divide by 2, and then depending on the observable, it's quite huge. And here you have the rapidity as a factorization scale, and you are doing next leading order. So my question is, the people that are using these impact factors, then, are they trying to vary this factorization scale?
Very nice. So you see, the point is what I try to hide here, or not to go in detail here, but it is related exactly to this. When they calculate the NLO impact factor, they leave the energy dependence contamination inside the coefficient. What does it mean? It means that if you look at this diagram, they look pretty much like a BK equation, right? Indeed, you see the impact factor evolution, the impact factor is multiplied by the BK type evolution equation, you see? Indeed, this impact factor, there are two contributions. One is purely NLO, and another one is exactly BK equation with the log, which is not conformal invariant. That is exactly BK inside the NLO. This means that it is energy dependence.
Yes.
But this energy dependence is already resummed by the leading order evolution equation.
Yeah, like the next leading order coefficient functions that show log of q squared, right?
Exactly. So you want to resum only once, not twice, right?
Yeah.
Or at least you want to find a way to separate what is the leading order summation with the impact factor and the next leading order summation with the impact factor. So for our purpose, this was achieved by considering this object. So if you introduce this counter term, you see you have this operator, the starting operator. At NLO, you realize that this operator is to be corrected by this object. If now you see you evolve this conformal composite operator, then this object and the impact factor does not depend on energy anymore. It's fully conformal invariance. If it depends on energy, it means that there is a scale. You change energy and then it's not anymore conformal because there is a scale dependent, it's energy dependent, right? So if instead you use this counter term, you turn off the energy dependence in the impact factor, you restore conformal invariance. Your evolution equation itself is conformal invariance up to beta function contribution. If you don't use this conformal composite operator, you would get contamination here of double log, which are not proportional to B, the beta function, 11/3 and C, right? Typical of the beta function. It's an extra contribution as a remnant that you're not using the proper operator in this order. So if you use this composite conformal operator, you restore conformal invariance of your evolution equation up to running coupling contribution, and your impact factor does not depend on energy anymore. This impact factor does not depend on energy anymore, and you don't have any more ambiguities.
Okay. Okay.
Indeed, let me just mention last things here. You see, if you consider gamma star scattering, and you consider NLO, then you see you have a leading order plus next leading order resummation, and then you have to convolute with the leading order impact factor and next leading order impact factor. But now this next leading order impact factor contains leading order type of logs. So a systematic way is to consider that conformal composite operator, and this energy dependence of this coefficient function is turned off, and it's only included in the matrix element. And that's why we were able to consider the full gamma star at NLO, because we know, I'm talking about analytically, not numerically. This is analytically done. Then you can perform last integration analytically, but there is no log of energy if not in the resummation. You see, you have a exponentiation of the leading order eigenvalues and next leading order eigenvalues, and the impact factor, leading and next leading, do not depend on energy. And you can do this only if you use this composite conformal operator in this OP language.
Okay, thank you very much again.
Thank you.
I guess nobody has another question. So we thank you very much, Giovanni.
All right,
And,
thank you for the invitation.
Yes, and we hope we can meet in the following years, maybe in person, right?
Yeah, that would be nice.
Yes, so thank you very much. Rafael, acho que pode parar a transmissão.
Tá certo, já vou encerrar.
So we're finishing here everything. And people are saying goodbye in the chat.
All right, I see the chat. Yeah, I